Hey everybody, this is going to start for us, again, still out of our AP Chemistry book. This is Chapter 9, and it's going to be sections 3 through 6. So again, out of the AP Chemistry book, Chapter 9, sections 3 through 6. As I look at this, it says in Chapter 8 we discussed, well, for my Chem 2 students, that's going to be back in Chem 1, we did discuss, or you should have discussed, bond dipoles. The bond dipoles for carbon dioxide are shown on this one, and it says just because a molecule possesses polar bonds does not mean a molecule as a whole will be polar. So we do have the carbon to oxygen bond itself is polar in this example, but the molecule as a whole is nonpolar. In this example right here for water, this one also has two polar bonds. The O to H is polar, but because these bonds, if you think about the Lewis structure for water, the Lewis structure, you're going to have a couple of lone pairs on oxygen. That's going to change your bond angle. So now these angles do not cancel each other, and the overall resulting dipole is created, and we do have a polar molecule. And here are several more examples. Just going over quickly, trying to keep it basic from Chem 1 standpoint of view. We looked at symmetry. And we looked at lone pairs on your central atom. So lone pairs of electrons on the central atom. And with those two right here, basically, if you're going to have a polar molecule, and this is going to be in general, I'm going to add asymmetrical here. So if your molecule as a whole is asymmetrical, and the example of that is right down here with your CH3Cl, if that other bond off a carbon would have been a fourth hydrogen instead of Cl, then it would have been symmetrical. But the chlorine itself throws the symmetry off of this particular molecule, making it polar. And then the other part for polar molecules, and this is an or kind of thing, so it can be asymmetrical or even the lone pairs on the central atom. As I look at that, ammonia does have lone pairs on the central atom. It is polar. And the one with just two atoms, the HCl, there's only one bond. It is a polar bond. Therefore, the molecule as a whole is polar. And then for nonpolar, it really needs to be both of these, not an or situation. So this is or over here. This is an and situation. We are looking for symmetry with our elements, and we are looking for no lone pairs on the central atom. And for these two right here, we do have that whenever we look at CH4, that is CCl4, and we also have that with BF3. So no lone pairs on the central atom, and all of the surrounding atoms are the same, which helps with its symmetry. So that is a recap from last year in general. We're going to now take that a step further, and we're going to get into our hybridization really quickly. Again, your notes that you had from the last section, I had you add one more column onto all of those electron domains, the shapes that you had, your bond angles, and then we're going to add hybridization to that. In this picture right here, they're just showing you how bonds actually form. We've got two different examples. If we split this right here, there on the left, you've got two hydrogens coming together. Notice the overlap region, very symmetrical there. And then the one on the right, you have hydrogen and chlorine, and they're showing you the p orbitals that you have right here. So hydrogen and chlorine, you do have an overlap region there between 1s and 3p. And then in the third example to the right, you have two chlorine atoms that are going to be bonding, and you can see the overlap region with the p orbitals there. So on the left, you have your s orbitals overlapping, in the middle, an S and a P overlap, and then on the right, 2 p orbitals are overlapping. And then this right here, hopefully you saw a diagram that looked like this last year, just showing you the bond formation and what's going on with energy. And it says the increased overlap brings the electrons and nuclei close together, decreasing electron repulsion. I'll kind of mark this up as a ABC. So in part A, there's really no interaction between the atoms. You are at a potential energy of 0. Once you start to get your overlap at point B, notice you have a drop in your potential energy. That is really good. And then at point C, where the perfect overlap happens, you have a balance between attractive repulses between one nucleus and the opposite electron cloud, and that vice versa goes true. That is a balance with repulsive forces with your electron clouds being close together. Notice that we are now at a minimum energy there. Everybody's looking for what gives me the lowest energy state. So if you can have 2 atoms that bond together, create a much lower energy state, they will do that. And then that last bullet point, it says if the atoms get too close, the internuclear repulsion greatly raises the energy. So if I were to add a point D, that's going to be point D right here, where the nucleus of one gets really close to the nucleus of the other. You can think of these 2 hydrogen atoms flying around. They bounce into a wall. They get squished together. Now the nuclei are like, whoa, 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 we are too close together and we want to repel. That'll blow your energy up. But they will spring back apart if they are allowed to. Now into our hybridizations. It says it's hard to imagine tetrahedral, trigonal, bipyramidal, and other geometries arising from atomic orbitals that we recognize. But it wants you to consider beryllium, for instance. I'm looking at my periodic table. Beryllium has 4 electrons. So in its ground electronic state, it would not be able to form bonds because it has no singly occupied orbitals. So 1s and 2s are completely filled up. The 2p orbitals are over there, but they're vacant. So again, beryllium would have 4 electrons, atomic number 4. But if it absorbs a small amount of energy, we get to promote an electron. So an electron from 2s is promoted to 2p, and now we have 2 different sites for other electrons to attach themselves. And these will not form the same bonds. So that 1 electron you have in 2s and the 1 in 2p will not have the same bonds. So mixing up our s and p orbitals yields 2 degenerate orbitals that are hybrids of the 2 orbitals. And we'll spend some time now talking about hybridization. The sp hybrid orbitals do have 2 lobes just like a p orbital. And you can see that there. But one of the lobes is going to be larger and more rounded than your s orbital. The degenerate orbitals will align themselves 180 degrees apart from each other. And this is going to be consistent with a linear geometry. So we did talk about a linear geometry. If there's only 2 atoms, it will be linear. In this orbital diagram right here for beryllium, notice we have brought over the hybridization. So instead of saying 1s, 2s, and then 2p, we do have our 2 orbitals right here that are hybridized. And they will be higher in energy than the 1s orbital, but lower in energy than the 2p orbital. So we call this hybridization simply SP. And we will get into more hybridizations. So now we're looking at boron. Boron, as I look at the periodic table, has 5 electrons. And if I looked at the orbital notation for boron, starting at the very beginning, you've got 1s, then your 2s fills up, and then within your 2p, we show all 3 orbitals for it. There is the 5th one, so they're just showing you what's going on within the 2nd energy level. That 1st energy level is full, it's stable, and it's going to stay that way. So coming right here to the bottom, we see our 2s and our 2p, the way that we see right here. And we're going to promote one of the electrons out of s, and now we have 3 total electrons, and this hybridization is called sp2. sp2. Just throwing out some numbers there for you with sp2. Again, that's an understood 1 at the top, so an understood 1. 1 plus 2 equals 3. So notice we do have 3 orbitals with 1 electron each. 3 orbitals with just 1 electron each. And if you go back to what we just looked at with beryllium, beryllium was an sp hybridization, so that's an understood 1 and 1. 1 plus 1 equals 2. We did have 2 orbitals with 1 electron each. So this is just showing you those 3 degenerate sp2 orbitals, how they are overlapping, and you can see where the lobe changes. Lobe size has changed. Moving on to carbon. Carbon again has 6 total electrons. But as I look again, they're leaving off the 1s, just trying to keep it simple, but 1s is going to stay intact. But with your 2s and your 2p, we do have another spot to promote 1 out of s, so the promotion has happened here. We have 4 total orbitals now that only have 1 electron each, and the final hybridization for it is sp3. Again, 1 for the s, 3 within p, 1 plus 3 is 4. So that is an sp3 hybridization. This is showing you the picture again of the sp3 hybridization, showing you the way the lobes change. Again, you can look at those. There's your 3-dimensional analysis there at the bottom and their bond angles. And it says for geometries involving expanded octets on the central atom. As a reminder, sulfur, phosphorus, xenon, they like to expand. Says now you've got to use your d orbitals for those hybridizations. They're showing you hybridizations here. If you promote out of s into the d sublevel, it really starts here at the bottom. So think of this as your starting point. Now we are moving an s right over into d, promoting it up this way, and then you end up with an sp3d hybridization, 1 for s, 3 for p, 1 for d, for a total of 5. And that's showing you the 5 degenerate orbitals there. And then there's also the look for 6 degenerate orbitals. So your hybridization can go up to sp3d2 for what we're going to talk about again. So that is 6 total areas in the last one, sp3d2, that you would have electrons. And here's our summary. This is what I want you to add to your notes where you left your column from last time. And I will highlight those parts for you. So as you're looking at yours and you've got 2 electron domains out in your hybridization column, the 2 electron domains is going to be sp. For 3 domains, it is sp2. For 4 domains, sp3. 5 domains, sp3d. And 6 domains is sp3d2. So when you look at your hybridizations, that is how it's going to line up with the electron domains and the geometries that we've already looked at. Now we're going to take these bonds further for the hybridization, and we're going to talk about 2 different ways orbitals can overlap, and we're going to look at sigma and pi bonds. So sigma bonds are characterized by a head-to-head overlap. So between your hydrogen and your chlorine, that is a head-to-head overlap. These are going to be cylindrical with your electron density about their internuclear axis. So head-to-head overlap is going to be very important for your sigma bonds. And also note, you'll see this often too, the symbol that we're using for sigma, whenever I write it, it kind of looks like this too. I try to keep it as close as I can to that. But again, sigma bonds are going to be a head-to-head overlap. And the other type are your pi bonds, and definitely pi, the symbol for pi should look familiar to you. This right here, though, our electron density is going to be above and below the internuclear axis, and this is a side-to-side overlap. So for our pi bonds, again, pi bonds right there, this is a side-to-side overlap. And now we're going to go in and look, well, how do you know what should be a sigma bond and what should be a pi bond, especially if you're not drawing out all of this stuff. Single bonds, to keep it simple, single bonds are always sigma bonds. Single bonds are always sigma bonds because the sigma overlap is greater, resulting in a stronger bond and more energy lowering. So definitely make sure you get this. Single bonds are always sigma. Your pi bonds are going to go with your multiple bonds. So in these two cases, we have a double bond in CH4. We have a triple bond in N2. So notice any of your multiple bonds, whether it's the second bond or the second and third bond of a triple bond, any of your multiple bonds after the first will be considered a pi bond. It's showing you another one right here. In this molecule of formaldehyde, we have an sp2 orbital on carbon overlaps in a sigma fashion with the corresponding orbital on the oxygen. Now, I don't plan on giving you drawings like this and making you pull back from that. I'm more interested, can you draw a proper Lewis structure? And then from the proper Lewis structure, can you tell me what's a sigma bond, what is a pi bond? So again, your unhybridized p orbitals will overlap in pi fashion, and that is the double bond. I'm just kind of underlining some important stuff here. Here's another example too. You got a triple bond. This is with C2H2, acetylene. And because of the triple bond, you will have one sigma and two pi bonds. One sigma and two pi bonds, because this is C2H2. We have two central atoms, so that's what it'll be around both of the carbons. Getting back to our resonance structures, they're showing you the resonance structure here for the nitrate polyatomic ion. Notice that that double bond can be between any of the surrounding oxygens since they are all oxygen. We do have a resonance structure here. It's showing you in reality each of the four atoms in the nitrate ion has a p orbital, and then those p orbitals on all three oxygens will overlap on the central nitrogen. This means that our pi electrons are not localized between the nitrogen and just one oxygen. Instead, they are delocalized. So when we talk about previously, whatever makes up that multiple bond, so a double bond in this case, it is those pi electrons that are delocalized and freely moving about to give your resonance. Here's one a little different. This is benzene. It's an organic molecule. we'll get to more organic later on. But in this one, you have 6 sigma bonds. And looking at it, notice that we do have double bonds in here. This is a ring, often called a benzene ring. But notice we do have a double bond, double bond, double bond. But that double bond, because it is all carbons, because if I were to draw this out and just making sure we label everything so that you know, it's going to look like this. So all those carbons are connected together with your 6 sigma bonds, but we do have a double bond, and a double bond like that. But because these are all identical and you have one hydrogen that is coming off of each of these, I'm not going to draw the H's in every single case, but you do have one hydrogen coming off of each of these. Those double bonds can transition. So now we're going to go look at the transition. And it says, in reality, the pi electrons in benzenes are not localized, but they are delocalized. They are delocalized. And the distribution of your pi electrons makes the molecule unusually stable. So benzene is a stable molecule. And again, that double bond, it can translate or move around between each of those sites.